Welcome back to the Deep Dive. Today, we're jumping into another sequence from the OEIS, the Online Encyclopedia of Integer Sequences. This is part of our ongoing series for, number theory students or really anyone who just loves exploring these mathematical patterns. Our target today, OEIS A000262. We're going to unpack this one and see where it leads. So the official description is the number of sets of lists. Okay, what does that mean? It's the number of partitions of one into any number of lists where a list means an ordered subset. That sounds a little dense, maybe. Let's break it down. Like for n0, it's defined as 1. Simple enough. For n1, the set is just 1. The only way to partition that is, well, just one list. One. So A1 is 1. But then it takes off. The first few terms are 1, 1, 3, 13, 73. See, grows pretty quickly. And to help us make sense of all this, its connections, its hidden depths, we're really lucky to have a Fields Medal-winning mathematician with us today. Welcome.
Thanks. It's great to be here. A000262 is, well, it's a really neat example of how combinatorial ideas can interlink in surprising ways. That definition, sets of lists, where each list is ordered. It's worth spending a moment on. Let's look at how we actually get those first few terms you mentioned.
Please do. I think N2, where A23 is probably the first place it gets slightly non-obvious.
Right. So for N2, we're partitioning the set 1, 2. Now, lists means ordered subsets. So 12 is one list, and it's different from 21. That's another list.
Okay, so the order within the list matters. That gives us two possibilities already.
Exactly. Those are the cases where we put everything into a single list. But we can also partition 1, 2 into multiple lists. The only way here is into two lists, 1 and 2.
So precisely. And because the definition says sets of lists, the order of those lists themselves doesn't matter. 1, 2 is the same thing as 2. It's just one way.
Got it. So the ordered list, 12, the ordered list, 21, and the set of list. Yes. Okay. A23 makes sense now. Good. Now let's try N3. The set is 1, 2, 3, and A3 is 13. We just apply the same logic, but there are more combinations.
I bet. How do we break that down?
We can think about the structure of the partition. First, what if we put all three elements into a single ordered list, like 123?
Okay, so you could have 123, 132, 213, 231, 312, 321. That's 3 factorial, right? 6 ways.
Exactly. 6 ways for a single list containing all elements. Now, what if we partition 1, 2, 3 into two lists? It must be one list of size 2 and one list of size 1, like, say, 12 and 3.
Right, so like 12, 3, or maybe 21, 3.
Yes, you need to choose which two elements go into the ordered list, and there are 3 ways to choose the pair, say, 1, 2. Then you need to order them 2 ways, 12 or 21. The remaining element, like 3, forms its own list, 3.
Okay, so choosing 12 gives 12, 3, and 21, 3. Choosing 1, 3 gives 13, 2, and 31, 2. Choosing 2, 3 gives 23, 1, and 32, 1. That's another 6 ways.
That's it. 6 ways for that type of partition. So we have 6 from the single list case, 6 from the list of 2 plus singleton case. What's left?
I'm splitting it into 3 lists, like 1, 2, 3.
Perfect. All singletons. 1, 2, 3. And since it's a set of lists, order doesn't matter. There's only one way to do that.
So 6 plus 1 is 13.
Yeah.
Okay. It works out. It's quite methodical.
It is. It requires careful bookkeeping. And you can imagine for N4, where a 473, it gets, well, significantly more involved.
I can definitely see that. We probably don't need to walk through all 73, but what kind of arrangements are we talking about for N4? Just the category.
Sure. For N4, you'd consider a single list of 4, like 1234. There are 24 ways to order those.
Okay.
Then partitions into 2 lists. This could be a list of 3 and a singleton, like 123. Yeah. Or it could be 2 lists of 2, like 1234. You'd count the ways for each type.
Right. Got to consider the ordering within each list and the choices of elements.
Then partitions into 3 lists, that would have to be 1 list of 2 and 2 singletons, like 12, 3.
Okay.
And finally, the partition into 4 lists, all singletons.
Yeah. 1,
2, 3, 4. Just one way for that.
Wow. So summing up the counts for 1233, 4, 12, 34, 12, 3, 4, and 1, 2, 3, 4 must give 73.
Precisely. The combinatorics gets richer with each step.
It definitely does. Thanks. That clarifies the core definition a lot. But you mentioned earlier, and this is where I think it's really fascinating, that A000262 isn't just about counting these sets of lists. It shows up in other places.
It absolutely does. And that's often the magic of these sequences in the OEIS. They act like mathematical fingerprints appearing in contexts that look totally different on the surface.
Like red. Give us an example.
Okay, well, Consider permutations. Thomas Waiter found an incredible connection. He showed that A and N is exactly what you get if you do the following. Take every single permutation of the numbers 1 to n. There are n of them. For each permutation, figure out its cycle decomposition, how it breaks down into cycles.
Like 1, 2, 3, 4 is 2 cycles of length, 2.
Exactly. Then, for that single permutation, multiply the lengths of all its cycles together. So for 1, 2, 3, 4, you do 2, 2, 4. Now, do that calculation, multiply the cycle lengths for every single one of the n permutations, and finally, add up all those products.
Add them all up.
Add them all up. The final sum you get is AN.
Whoa. So for N4, you'd look at all 24 permutations, calculate the product of cycle lengths for each one, and add those 24 numbers, and you get 73.
You get exactly 73. It's a completely different way to arrive at the same number. It tells you there's some deep structural relationship between partitioning into ordered lists and the cycle structure of permutations.
That's pretty mind-blowing. Are there others?
Oh, yes. There's another interpretation by Dennis P. Walsh involving something called chain gangs.
Chain gangs. Sounds intriguing.
It does, doesn't it? So for a set S with n elements, a chain gang is basically a way to put a partial order on S, where every element is comparable to only elements within its own chain. It's a bit abstract. But the number of distinct chain gangs you can define on a set of size turns out to be A. For N2, say the set is AB, there are 3 chain gangs. One where A and B are unrelated, one where A comes before B, and one where B comes before A. These correspond to the 3 ways we found earlier.
So A, B, A, B, B, A, B, 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 A. Okay, I sort of see the parallel to 1, 2, 12, and 21 in a way. It's another structural interpretation.
Exactly. It's about how you structure relationships within the set.
That's quite theoretical. Is there anything maybe a bit more concrete, something easier to visualize? I think I read one that stuck with me.
You might be thinking of Enrique Navarrete's interpretation. It's a really nice one. He showed that for N0, AN is the number of ways to do this. Take N people, split them into some number of non-empty groups, have each group sit down around a circular table. Then, from each table, select exactly one person.
Yes, that's the one. Splitting people into groups, arranging them in circles, and then picking a representative from each circle.
The total number of ways you can perform that whole procedure is AN.
That just seems so unrelated to ordered lists or permutation cycles or chain gangs.
Right.
But it produces the same numbers, 1, 3, 13, 73. It really drives home how mathematics finds these unifying patterns.
It really does. It's a beautiful illustration of combinatorial equivalence. And beyond these direct interpretations, the sequence itself has some very important mathematical properties and connections to other famous objects.
Okay, like what?
Well, for one thing, A000262 is what mathematicians call d-finite.
D-finite, what does that signify?
It basically means the sequence satisfies a linear recurrence relation with polynomial coefficients. It's a kind of regularity. Specifically for A000262, the recurrence is AN to N-1, AN-1, N1, N-2, AN.
Whoa, okay, so if I know AN1 and AN2, I can calculate AN using that formula.
Precisely. If you know A23 and A313, you can calculate A4. Let's see, 24 to 1, A3, 4 to 1, 4 to 2, A2, 91, 18 equals 73. It works.
That's powerful. Gives you a computational handle on the sequence.
It does. D-finiteness tells us a lot about the sequence's structure and how it behaves. It's not just a random string of numbers. It also means it has a nice generating function.
Generating functions. Those are like compact ways to store the whole sequence, right?
Exactly. In this case, the exponential generating function, EGF, is remarkably simple. It's x1x.
E raised to the power x over 1x.
Yay.
That function somehow encodes 1, 1, 3, 13, 73.
It does. If you were to expand that function as a power series in x, the coefficient of xnn would be exactly an. Generating functions are incredibly useful tools in combinatorics for finding properties, recurrences, and connections.
Okay, so it has this internal structure, the recurrence, and this compact representation, the EGF. Does it link externally to other well-known sequences or numbers?
Oh, absolutely. It's deeply connected to some very fundamental combinatorial numbers. There's a formula relating AN to the Stirling numbers of the first kind and the Bell numbers.
Stirling numbers and Bell numbers. Wow. Those are heavy hitters in combinatorics. Bell numbers count partitions of a set, right?
Yes. A000110, the Bell numbers, count the ways to partition a set of n elements into non-empty subsets. And A008275, the Stirling numbers of the first kind, relate to permutations and cycles. The formula is AN sum k 00 baro k. So you take the absolute values of the Stirling numbers, multiply by the corresponding Bell number, and sum them up.
That's the one. It shows that A000262 is intimately tied into these basic ways of counting arrangements and partitions. It's not some isolated sequence, it sits at a crossroads.
It really seems like a bridge between different concepts. You also mentioned, was it Laguerre polynomials? That sounds like something from a different field entirely.
It does, doesn't it? But yes, there's a connection. AN and 1. Laguerre N1, 1, 9 is 1 for N a 1. Laguerre polynomials, Ln, alpha, x, are solutions to certain differential equations, and they pop up in places like quantum mechanics solving the Schrödinger equation for the hydrogen atom, for example.
Okay, now that's just wild. A sequence counting sets of lists connects to quantum physics via these special functions. It speaks to the surprising universality of some mathematical structures. The patterns recur across disciplines.
Are there any other, maybe simpler properties of the numbers themselves, like patterns in the digits or divisibility?
There are a couple of neat ones if you look at the sequence. 1, 1, 3, 13, 73, 411, 2761. Notice the last digits.
1, 1, 3, 3, 3, 1. Oh, wait. 73 ends in 3. 411 ends in 1. 2761 ends in 1. The next one, A6, is 21193, ends in 3.
Yeah.
It seems like they always end in 1 or 3.
Exactly. All terms are concurrent to 1 or 3 modulo 10. It's a simple observation, but kind of striking for a sequence that grows so fast.
That is curious. Any others like that?
There's a deeper one, originally a conjecture by Peter Bala, which is now proven. It states that for any integer k equals 2, the difference between terms k steps apart, an plus kan, is always divisible by k.
Divisible by k, so an plus 2an is always even, and an plus 3an is always divisible by 3.
That's right. It implies a kind of periodic behavior when you look at the sequence modulo k. It reveals a hidden layer of structure.
It's really elegant. So wrapping this all together, we have this sequence A000262 defined one way, but appearing in many contexts. Permutations, partial orders, even this people at table scenario. It has internal structure, connections to major combinatorial numbers, special functions, and these neat divisibility properties. What's the big takeaway here for us, as learners trying to get a feel for number theory and combinatorics? How does seeing all these connections help?
I think the biggest takeaway is seeing the profound unity in mathematics. When the same sequence answers seemingly different questions, it's not just a coincidence. It signals that there's a shared underlying structure, an isomorphism connecting those different areas. Understanding A000262 as sets of lists might be intuitive one way, while understanding it via permutation cycles might offer computational advantages, and seeing the connection to Bell numbers might place it within a broader theoretical framework. Studying these multifaceted sequences gives you, a richer toolkit. You learn to recognize patterns across different domains. It shows that breakthroughs in one area might come from insights gained in another, seemingly unrelated one, just by following the trail of numbers. It encourages you to look beyond the surface definition.
That makes a lot of sense. It's like learning different languages to describe the same core idea, and each language gives you different insights. We started with A000262 as sets of lists, saw it mirrored in permutation cycle products, visualized it with people around tables, and connected it to huge concepts like Bell numbers and even Laguerre polynomials. It's quite a journey for one sequence.
It really is. And perhaps the final thought to leave you with is this. How many other sequences in the OEIS or patterns you encounter in mathematics have these hidden connections waiting to be found? It suggests that just by carefully observing numbers and asking why they appear in different places, we might uncover deep truths about the structure of mathematics itself. What undiscovered links are still out there?
A fantastic question to keep in mind. Thank you so much for taking us on this fascinating deep dive into A000262 today. And thank you all for joining us.